In this section, we're going to be going over the precise definition of a limit. So previously, the wording that we used for limits was kind of vague. We said something like x is close to 2 or x approaches 2, and f of x gets closer and closer to some limit L. So that doesn't really work as a great definition. So we're going to actually come up with a better definition of what kind of these words like closer and closer actually mean. Okay, so let's take a look here. So we have this graph, and we have said previously that we can use this notation. The limit of f of x as x approaches a equals L. So that would be this particular graph. We have a hole here, f of a does not exist, but the limit would equal that y value L. So now we're going to define what it means to, like, the terminology closer and closer to L. So we can get f of x, we can get these y values closer and closer to that y value of L. And what we're going to do is we're going to call that value epsilon. So it's the Greek letter epsilon. Epsilon is going to be a positive number, so greater than 0, and it's going to represent the distance between f of x and L. Okay, so we're going to be either told an epsilon, or we're going to come up with an epsilon, a distance for the function, getting closer and closer to the limit, by making the x value sufficiently close to a. And this distance between x and a is going to be called delta, and delta is also a positive number. So it's the same concept on this graph. We're going to have these x values getting closer and closer to that a value, that as x approaches a. Okay, so epsilon is essentially a y distance, and delta is an x distance. So typically, taking a look at this next thing here, we can be told how close we want the function values, the y value, to be to that limit L, which is some positive number epsilon. So for example, we can be told that epsilon has to be 0.1. If we're told that epsilon is 0.1, what that means is the function has to be within 0.1 of the limit number. So the y values for the function have to be within 0.1 of the limit. So when we have that, we're going to have to give another positive number delta, such that if we are within delta units of a, then the function values will be within epsilon units of L. Okay, so let's try to take a look and make sense of this, because probably a little bit confusing using all of the letters. So if we have this same little function that we just had on that first page, if we are epsilon units away from L, that means we can go in two directions, right? We can be epsilon units greater than L or epsilon units less than L. If we are epsilon units greater than L, then that's L plus epsilon. And if we are epsilon units less than L, then it's L minus epsilon. Okay, so just remember, these are all just essentially representing numbers. So these y values will correspond to their own x values. So notice that this epsilon distance is the same above and below the L value, right? It's L plus epsilon and L minus epsilon, same distance. But when you take a look and it corresponds to the x, you can see that those x distances are not the same on both sides of the a value, and that's typically what's going to happen. So if it was perfectly even, we would say that this value might be a minus delta, and this one over here might be a plus delta. So that's the x distance. But since they're not perfectly even, that delta value is not going to be, it's not going to be set up like a minus delta and a plus delta. We're going to be finding in some of these questions the delta value, and the delta value is typically going to be the smaller one. So this side is obviously smaller than this side, right? So that side will be the delta value. So I'm going to write this as a plus delta because it's greater than a, so plus. So we choose that smaller distance to find the delta. So the delta value would be whatever the difference is between those 2 points right there. So let me just move this over a little bit. I'll say that this value is a plus delta, meaning this distance here is a distance of delta units. So the reason why we have to choose the smaller one and not the bigger one is because if we chose the bigger one, like let's say this distance from here to A was 4. If we took that distance and added that 4 units to the right of A, maybe that would be right here. And then if we went all the way up to the function and found the y value, that y value is no longer within our range of epsilon for the y coordinates. So that's why we always have to choose that smaller distance for the delta. Okay, so essentially what we're doing here is we're going to be finding a delta value, so that if the distance between any x value and a is less than that delta value, then the distance between f of x and the limit is less than epsilon. And here is the actual definition here using our mathematical notation. And once again, hopefully this starts making, hopefully conceptually it kind of makes sense, and then we'll see a bunch of examples coming up. So for the precise definition of a limit, let f be a function defined on some interval that contains the number a, except possibly a itself, because we know there could be a hole at that value. Then we say that the limit of f of x as x approaches a is L, and we just write it just like that using our limit notation. And we say that that is, that's the limit if, here's the important part, if for every positive epsilon there is a positive delta, such that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. So that all this means right here is a distance, right? Absolute value, technically, if you're taking the absolute value of two things being subtracted, that is just the distance between them. So if that's the case, then the distance between a y value and the limit is less than epsilon. So it looks a little bit confusing, but once you know that the absolute value for two numbers being subtracted, all that means is a distance between them. So the distance between the x values is less than a certain number delta, implies that the distance between the y value and the limit is less than some number epsilon. Okay, so let's go ahead and actually use this now. For example, let's use the given graph of f of x equals the square root of x to find a number delta such that if the distance between x and 4, so the absolute value of x minus 4, is less than that delta, then the distance, or the absolute value between the square root of x minus 2 is less than 0.4. So here we have this graph, so we can make some sense of it now. We have the graph, we have the blue function here is the square root of x, and we are told epsilon is 0.4, right? Because in the setup, f of x, the absolute value of f of x minus L less than epsilon, that is this one right here. The one up top is the absolute value of x minus a less than delta. So we can see that epsilon is 0.4. So I'll write it over here. Epsilon is 0.4. And here is our limit. Our limit is 2. So it's very important to just know this setup so you can figure out what epsilon is, what your limit is. And while we're up here, I'm just going to say a equals 4. Okay, so now we can see what it means graphically. The limit is 2, so there is your limit of 2. Epsilon is 0.4, so this is your limit plus epsilon. 2 plus 0.4 is 2.4. And this number is your limit minus epsilon. 2 minus 0.4 is 1.6. Okay, so then we create the horizontal lines, we go over to the function, find their corresponding x values. So you can see their corresponding x values are question marks. So this is going to be part of what we are actually finding here. And then we can also see that this a value is 4. And now what we're going to do is we're going to try to find a delta. We're going to try to find a delta such that if we add delta to 4 or subtract it from 4, then it is guaranteed to give us y values between 1.6 and 2.4. So going into this, what I like to do is I like to take a look at this right here. We have two options for delta. Either delta is going to be this distance right here, or delta is going to be this distance right here. So delta is going to be one of those numbers, and it's going to be the number that is the smallest. Okay, so we have to figure out both of those distances, and our delta is going to be whichever is the smallest one. So our first thing that we're going to have to do then is figure out what are these two question marks. So let's go ahead and do that. And even before I do that, I'm going to go ahead and just write something down. Okay, so I just want to write down in words what we're going to be doing, finding the number delta that corresponds to epsilon equals 0.4, and the definition of a limit for f of x equals radical x. So what we're going to do here is we are going to start with this right here. We're going to start with the absolute value of radical x minus 2 is less than 0.4, so let's go ahead and write that down. Okay, so we wrote this down, and what this is going to do when we solve this for x, this is going to find the question mark x values. That is going to find these values right here for us. Okay, so we have to remember how to solve an absolute value inequality. If you have the absolute value of something less than a number, what you do is you drop the absolute value bars, you make it less than the number, and then you also make it greater than the negative version of that number. Okay, so that's pretty much going to happen every single time for a question like this. For these types of questions, you drop the absolute value bars and you also set it to be greater than the negative version. And then we solve for x. Solving for x means we have to add 2, because we need x by itself here in the middle. We have to get rid of negative 2. We add 2 to everything, and we get radical x is between negative 2 and 6. And now to get rid of the square root, now we square everything. So negative 2 squared is 4. That gives us just the x in the middle. And then 6 squared is 36. And whoops, sorry, I actually messed this up. Let me just go back and erase some of these values. I put 4, and it was actually 0.4. So let me just go ahead and fix that. 0.4, I was wondering why those values were so big. Okay, so 0.4, negative 0.4, same idea though. Now we're going to add 2 to everything. That's going to give us 1.6. Add 2, we get 2.4. And now we square both sides. And we get that x has to be between 2.56 and 5.76. So that is what these values are right here. That's what these question marks are. So what I'm going to do, I'm just going to erase some of this stuff that's in here. And I'm going to say this question mark is 2.56. And this one is 5.76. And if we take a quick look at it, that makes sense because One of them is less than 4, the other one's a little bit greater than 4. So now it's pretty simple. Now all we have to do is figure out the distance for that red line, the distance for that light blue line, and the smaller number is going to be our delta value. Okay, so let's go ahead and do that. I'm going to call that the first one, the left endpoint distance from 4, and I'm going to call the other one the right endpoint distance from 4. So how do we calculate these distances then that are right in here? We just have to subtract. So the first distance is going to be 4 minus 2.56. So 4 minus 2.56, that's going to give us 1.44. And then the other one is going to be 5.76 minus 4. And notice I'm just doing smaller number minus large number minus smaller number just to make sure that we get the positive number out. And we get 1.76. So those are the two distances, and like we've been saying, we choose the smaller one. And that means that delta is going to equal the smaller number here, the smaller distance, which is 1.44. And now I'm going to go up and just restate this beginning right here. And I'm just going to replace delta with 1.44. So I'm going to say, so if the distance between x and 4 is less than delta, which is 1.44, then the distance between the function and 2 is going to be less than 0.4. Okay, so one more time, let's make some sense out of this. So we found our delta. So that means if we have a number less than 1.44, and we add or subtract it from 4, then it guarantees that the y values will be between 1.6 and 2.4. Okay, so hopefully that conceptually makes sense. The math is really easy, but conceptually is a little bit more difficult. All right, now let's actually do a proof here. Let's prove that the limit of 4x minus 5 as x approaches 3 equals 7. So we know it equals 7 because we can just go ahead and plug in the 3. 4 times 3 minus 5 equals 7, but we're going to prove it using the epsilon-delta proof. So even though these questions can be a little bit confusing, the good thing is that we actually do most of them the same exact way following these steps. So the first thing you're going to want to write down is let epsilon be a given positive number. And then you're going to want to write down what we're doing. So we're always going to be finding some delta that's positive, such that if the absolute value of x minus 3 less than delta, if that's true, then the absolute value of the function minus the limit, 7, is less than epsilon. Okay, so you're always going to want to have this setup, and it's the same setup that we were doing before, is absolute value x minus a less than delta, and absolute value f of x minus L less than epsilon, and that is for the limit as x approaches a of f of x equals L. So all I did was use this question, and I found out what my a is, my f of x, and my L, and I just plugged them into here. Okay, so let me just erase that so it's not too much on one page here. So what we're going to do now is we are going to start with the absolute value of f of x minus L less than epsilon, which is this one. And then we're going to simplify it until it looks like the absolute value of x minus a less than delta. And we do this because then we're going to find delta in terms of epsilon. So when we originally wrote let epsilon be a given positive number, so we're just assuming that epsilon is some positive number. We don't know what it is, but we can choose it to be whatever we want. But right now we're just going to leave it as epsilon. So step 1 here is going to be find delta. So it's going to be delta in terms of epsilon. Okay, so like I mentioned, we're going to start with the absolute value of the function minus the limit is less than epsilon, and now we need to simplify it until it looks like this one up here. Okay, so first it's pretty obvious that it can simplify to 4x minus 12 less than epsilon, because negative 5 minus 7, negative 12. And now we have to say, okay, how can we get 4x minus 12 to look like x minus 3? We can do that by factoring out a 4, right? So we factor out a 4. Since it's a positive 4, we can factor it right out front. And if we factor it out, GCF style, then we're left with x minus 3. All we have to do now is divide both sides by 4. We get the absolute value of x minus 3 is less than epsilon over 4. Okay, now it's pretty clear that this looks exactly like that. They both say the absolute value of x minus 3 is less than something. On the right side here, we have epsilon over 4. And then on the right side here, we have delta. What that means is that delta, we choose delta to be epsilon over 4. Okay, so whatever epsilon is, delta is going to be epsilon divided by 4. And the second step here, before we take a look at this graph, the second step is going to be to show that this delta value works. So we need to show that it works by going back and essentially plugging it in. To do that, we're going to essentially do what we just did, and we're going to start with the absolute value of the function minus the limit, and we're going to simplify this so it looks like right here, and that's going to end up being 4x minus 12, and we factor out the 4, so pretty much restating what we just did. Except once we get to this point, we get it to be something times the x minus 3 that we want it to be. Now we are going to say that it's less than or equal to, we know, before I write it in, we know absolute value x minus 3 is less than delta. So if we multiplied both sides by 4, then this statement would still be true, and it would end up as 4 delta on the right, right? So that's what we're going to end up writing right here. 4 delta, it's whatever that number was right out front. And now we're going to replace delta with what we chose it to equal in terms of epsilon. So we said that delta is epsilon over 4. The 4's cancel, and we are left with epsilon, which is what we wanted. So we just showed that this is less than epsilon, which is what we essentially started with, but we showed that it worked when we used a delta value of epsilon over 4. Okay, so once again, a little bit, you kind of just have to remember the steps for this one. So let's go ahead and finish it off. We have to finish it off by saying, I'll say thus, if the absolute value of x minus 3 is less than delta, then the absolute value, write it on the next line, then the absolute value of 4x minus 5 minus 7 is less than epsilon. And then the last thing that we say is, therefore, by the definition of the limit, and then we go ahead and just rephrase what our limit is. The limit as x approaches, what was it, 3, of 4x minus 5 equals 7. Okay, so these steps, once again, the math is not very difficult, right? The concepts are a little bit difficult, but when you're proving a limit like this using epsilon-delta proof, you should follow these steps exactly, each and every time. Okay, and I'm just going to write up here just for future reference. I'll put epsilon-delta proof because that's what people tend to call them, but it's the precise definition of the limit. Okay, let's take a look at the graph now just so we can make some sense of it. So here's the graph of 4x minus 5. We know that that's a linear function, so it's just a line. And we have our limit of 7, and then we have our limit plus epsilon and our limit minus epsilon. So we have a distance of epsilon here and epsilon here. And then what we did is we go back over here to find their corresponding x values. And then we have 3 minus epsilon and 3 minus delta and 3 plus delta. So if we choose any number that's less than delta, that'll be within this little interval next to 3, then it guarantees that the y values will be within epsilon units of 7. Okay, so this one was just very generic, and we didn't actually have an epsilon, we just knew it's some positive number. Okay, so let's do another one here. Prove that the limit of 3x plus 5 equals negative 1, and that's when x goes to negative 2. So let's go do this one a little bit faster. Restart the same way as the other one. We know we're doing epsilon delta proof, so we're going to let epsilon be a given positive number, and we're going to find a positive delta such that if x plus 2 less than delta, then the absolute value of 3x plus 5 plus 1 is less than epsilon. Okay, so hopefully you took a look at this and said, why is it x plus 2? That's because it is, it's x minus, it was going to negative 2, so it's x minus negative 2, which we know just becomes x plus 2. Same thing with the epsilon one. It was minus a negative 1, which just plus positive 1. Okay, we're going to start this the same way as before. We are going to find delta. And we're going to do it starting with the function, the absolute value of f of x minus L less than epsilon. So that's going to be the absolute value of 3x plus 5 plus 1 less than epsilon. We start with this. We're going to make it look like this one right here and figure out what delta is going to be in terms of epsilon. So we simplify it, we get 5 plus 1, so 3x plus 6. And then we're going to go ahead and factor out a 3. I'm going to factor that right out front. That leaves us with x plus 2. And now we recognize, okay, here's our x plus 2, matches this x plus 2, which is good. We divide both sides by 3. And we get the absolute value of x plus 2 is less than epsilon over 3. So that means we go ahead and we're going to choose the delta value. We found delta is going to be epsilon over 3. So there is delta in terms of epsilon. And now we're going to go ahead and show that it works. Okay, so we essentially start the same exact way. We start with, move it over a little bit. Start with absolute value 3x plus 5 minus a negative 1, or just plus 1, is, and now we're going to simplify this, and simplify it the same way we just did. That's 3x plus 6 in the absolute value. We factor out a 3 times the absolute value of x plus 2. Once we get to that setup right there, what we're going to do is use the fact that the absolute value of x plus 2 is less than delta. We can multiply both sides by, in this case, 3. And that's what we write, is less than 3 delta. And then we're going to replace delta with what we chose that delta is going to be, which is epsilon over 3. So that's 3 times epsilon over 3. The 3's cancel, and we get epsilon, which once again, that's our goal to show that it works, is to show that this is less than epsilon using our delta value in terms of epsilon. Okay, so we just showed that, and that's pretty much it. Now we have to do a little concluding statement. And we say, thus, if the absolute value of x, x plus 2 is less than delta, then we know that the absolute value of 3x plus 5 plus 1 is less than epsilon. So that's what we just proved. So now we say, therefore, by the definition of the limit, and we essentially just repeat what the question was originally asking, which was the limit as x approaches -2 of 3x plus 5. We now know that that equals -1 because of the definition of a limit and our proof. Okay, let's do 2 more examples here, 2 more shorter examples. And actually, I'm gonna skip doing this particular problem. I'll fill it in for the filled in notes and have it posted if you want to take a look at it. But I will skip this one for now for time's sake, because you'll see that a lot of it's actually done using a graph, using a graphing calculator, which we're not using. So I'm just going to skip that one. Okay, so let's do one more example here. Let's use the given graph of f to find a number delta, such that if the absolute value of x minus 2 is less than delta, then the absolute value of f of x minus 8 is less than 0.4. So this one is a lot easier. We're just trying to find delta this time, trying to find a number delta, and we're given the graph, which is great. We are not given the function itself. We're just told it's f of x, but we're given the a value, we're given the limit value, we're given epsilon, and what makes it easy is that we're actually given these values right here on the x-axis. So we can see that the L is 8, so here is 8, and then we add epsilon, we get 8.4. We subtract epsilon, we get 7.6. They correspond to an x value of 1.9 and 2.3 around our a value of 2. So if we want a value delta, then all we have to do is find which distance is shorter. Is 2 minus 1.9 shorter? Is 2.3 minus 2 shorter? Whichever one's the smaller number is our delta. So let's go ahead and do that. So 2.3 minus 2 is obviously 0.3, and 2 minus 1.9 is 0.1. So the smaller number is 0.1. So that is our delta. Delta is 0.1. Okay, so that one was actually just as easy as that. We just have to remember to always choose that smaller x distance. So if we want to, we could write this out, and we could say now, if the absolute value of x minus 2 is less than 0.1, then that means the absolute value of f of x minus 8 is guaranteed to be less than 0.4, which is the epsilon value. Okay, so as long as the distance between the x value and 2 is less than 0.1, that'll guarantee that it's somewhere in here. That will guarantee that the y value corresponding to it will be between 7.6 and 8.4. Okay, so that is it for this section.